Industrial Hygiene, Chapter 8, Particulates. A portion of this presentation is drawn from other sources. Your book has very good technical details about particulates and particulate sampling, but in my opinion, it's a little too technical, at least for a survey-style course like this one is, which is a fundamentals course. So I'm going to try to explain some of those details about particulates and why we're concerned about them in a little more detail, using a little less technical language that may hopefully help you understand particulates in the air. Particulates are a very complex subject that not a large percentage of industrial hygienists truly understand, but you still need to have an understanding of the basics of particulates in the workplace. Now, one of the problems I have is I've been dealing with particulates for a long time. The language that is used, and your book points it out in a couple of places, has changed over time. So micron or micrometer both mean 1/1,000,000th of a meter. Micron is the older term. I tend to use them interchangeably. They do both mean the same thing, but I don't want you to get confused. If I say micron or micrometer, it means the exact same thing. I'm not talking about two different things at that point. Particulate matter, particulates, and aerosols. Particulate is the older term. Particulate matter is one of the more preferred terms, and the other generic term that essentially discusses things that are solids or liquids in the air is aerosols. So particulate matter, particles, or aerosols or particulates all mean the same thing. So once again, I have a tendency to try to slip back into the older language because I'm used to using it, but I don't want you to get confused. If I say particulate matter, particulates, or aerosols, I'm talking about the same thing, which is solids or liquids fine enough to be inhaled in air. One of the new areas of research, and your book has some interesting things about nanoparticles. Nanoparticles or manufactured nanoparticles are a relatively new thing. However, nanoparticles as an incident being produced as part of a process, not necessarily intentionally, have been around for a long time. There's quite a bit of research on the ultrafine or submicron particles that were produced not necessarily intentionally in the past. If you talk to somebody, they may refer to ultrafine particulate matter or submicron particulates. Those are just older terms that we use for nanoparticles. They're essentially the same thing. There's a little bit of difference, but not a lot. Kind of a notation on size, a meter, which is approximately three feet or a yard. A thousandth of that, which is the fine line. If you have a ruler that has millimeters and centimeters on it, it's the fine line, is a thousandth of a meter. A micrometer is 1,000th of a millimeter. So you're talking a micrometer is a millionth of a meter. And there are 1,000 nanometers in a micrometer. So when we start talking about those submicron particles, if you have something that's a half micron in size, it's 500 nanometers in size. A nanometer is also 10 to the -9th or 1/10000000th of a meter. The other phrase that I sometimes use that gets a little confusing, cut diameter. When we talk about, your book goes into some description of the fact that particulates in air is really a geometric distribution. To describe the center of a geometric distribution, we use the phrase cut diameter. Basically, it's the point at which 50% of the particles are larger and 50% of the particles are smaller. I'm not going to go too much into that in this lecture. If you want to learn more about it, your book does describe that in fairly good detail. I don't believe that that's an appropriate topic for something where we're just trying to introduce you to particulates, however. So how do we define that particulate matter? Small discrete particles of matter or liquid droplets in the size range of 0.001 that would be tenths, hundredths, thousands. So 1 nanometer or 0.001 micrometers to 100 micrometers AED in diameter. We'll talk about what that AED means in a minute. It's aerodynamic equivalent diameter. Since the stuff that's in the air isn't really uniform in either density or size or shape, we use a convention so that you can talk about it in a uniform manner with regards to where it's going to deposit or how it's going to behave. Okay. Once we start getting below 1 micron in size, you start moving away from things that behave like solids or liquids to things that start behaving more like gases. The closer you are down to the end of that range, that 0.0, that 1 nanometer, the more like a gas things behave. There's some debate as to what that bottom number really should be. If you read some other texts, the number ranges from 0.02 or 0.05 down to the 0.01 that they use in your textbook. All of those are kind of acceptable. I don't want you necessarily to have to memorize what that bottom of the range is. When we talk about nanoparticles in a little bit, NIOSH defines that as 50 nanometers or less in dimension. That would be 0.05, that number that is often referred to the point at which things start behaving differently. So what does an aerosol look like? When we talk about aerosols, remember aerosol, particulate matter, those are the generic terms that we use to talk about stuff in the air. A lot of times if you just kind of try to visualize it in your brain, you probably think about balls of stuff floating in the air. But in truth, aerosols have a range of shapes. As you may have noticed when we looked at the microscopic slides from last week's lab, certain types of pollen and mold spores look like little spiky balls. That little those spikes add a lot of surface area relative to the volume, to the mass, and so if it's a spiky ball, it may behave slightly differently than if it's a smooth sphere. Oh, by the way, these are dryer balls, just in case you're curious. Sometimes they don't have a well-defined shape. Some things are cubic. Some things are just kind of a smear of stuff. Again, if you remember looking under the microscope, you saw stuff that was round and stuff that was odd shapes. That's all stuff floating in the air. So again, we have to adjust. Something that looks like this that's floating in the air is going to behave differently than something that's a sphere. And by the way, that's a natural sponge. So the way that we handle this, the way we try to describe them so that when we talk about a particle of a certain size, we're talking about the way that it behaves, we use that aerodynamic equivalent diameter. It's a convention that we use to try to express the behavior of particles in a uniform manner. And basically what it is you take the original particle, you adjust its size and density so that the particle is the equivalent to the shape of a sphere and has a density of 1. So if I have a particle that's a perfect sphere but has a density much greater than 1, like a metal fume, it behaves as a much larger particle relative to, say, something that's a wood dust, which is predominantly air, which is much lighter and cubic in nature. So I have to be able to talk about these different types of particles so that when I'm talking about collecting them, where they're going to fall, and the health effects, I'm talking about the same sorts of things. And so that's where the AED comes in. It allows us to talk about things in a uniform manner. Now, particulates are considered to be a hazard when suspended in air, forming an aerosol, which can then be inhaled. In order for us to breathe something in, it generally has to pass within about 9 inches of our mouth or nose. Okay, so when we start looking at particles in the air and we talk about sampling in the breathing zone, that's a 9-inch sphere kind of centered around the bottom of your nose, hemisphere, a half sphere, based on going out 9 inches from basically the base of your nose and then drawing a sphere around that. The general convention is particles greater than 100 microns AED in diameter tend not to remain suspended in the air long enough to present a hazard. In other words, it's kind of like throwing a rock in the air, it falls down quickly. Some of those particles can be breathed in, but they're almost always taken out in the very entrances of your nasal passages. And so they're readily removed and therefore don't present a great hazard. This is based on physical size, not AED, but it gives you some feel for the different size of things. For example, molecules kind of start down here somewhere in this fractions of a micrometer from about 5 nanometers or 50 nanometers or so, 5 nanometers or so on down. Viruses, which we know we can readily inhale, range up to almost 1 micron. Bacteria can be as large as a little over 10, but anything less than 10 has the potential for us to breathe in and get to our deep lung. That's why if a nebulizer, if you're familiar with a nebulizer, if you know anybody that has asthma or other breathing issues, they have an inhaler. Sometimes they call those nebulizers. They're designed to deliver a dose to the deep lungs. That's why their drops are relatively small. We talk about if you go to the beach is made out of silica. We've talked a bit about silica and silicosis before. If anybody that lives near the beach or where sandy soil is why don't they have all developed silicosis? And the answer is your standard beach sand is greater than 100 microns in size or larger. And so we tend not to inhale it. Same thing with rain. Why don't you drown while you're in the rain? Because raindrops are large enough that we tend not to inhale them. So this is a chart. It's actually out of your previous book that kind of gives you a feel for the size of some different things. When we look at things that are greater than 100 micrometers, AED, are not readily inhaled. Things that are between 10 and 100 tend to collect in our upper airways and our middle airways. Things that are 10 microns on down have the potential to get into our alveoli. Now, the critical factors that play into how much of a hazard a particulate might present are standard doses there, concentration of particles in the breathing zone, as well as the length of exposure time, concentration and time, dose, as well as the type of particulate and the size of particulate. The size of particulate dictates where within the respiratory system you can expect it to be collected or fall out. And the type of particulate tells us what sort of effect we might expect it to have. Now, as part of your assignment this week, we're going to look at some of those biological exposure effects based on the different types of particulates, whether it causes an irritation effect, it's an allergenic effect, or some sort of systemic effect where it dissolves and gets carried elsewhere. So the type of particulate is an important factor. When we look at dusts, there's a number of different types of dusts. This is a summary of a chart that you have in your book. Your book also tells you a little bit more details about what these types of dusts are. Since I expect you to be able to read over that, and in fact you will have to in order to answer some of your questions, I'm not going to go over it into too much detail now. Dusts are generally solid materials for the most part. Mists are liquid droplets. Fumes are what we call condensation aerosols. Basically, it's something that I heated up past its flash point, so it moved from a solid to a vapor and then condensed back down. Often found in metal fumes are common. Of course, biological agents, and then smokes. Smokes are materials put off from the incomplete combustion of materials. If something burns completely, if it's an organic compound that burns completely with oxygen, I get carbon dioxide and water. If it doesn't burn completely, I get carbon chained material side stuff that's relatively small in size, and that's my smokes. So length of time with regards to exposure, if it's an allergenic agent or an irritant, it may only take a few seconds, an acute exposure. If it is a chronic agent, like pneumoconiosis, pneumoconiosis simply means that you have enough dust in the air to start causing damaging and scarring of the lungs. That may take a long time or years. We focus on two particular pneumocotic agents that cause what we call progressive fibrotic lung disease, silicosis and asbestosis. And basically what happens is those don't get cleared from your lung very well, and they persist and cause ongoing scarring and damage long after the initial exposure may have occurred. You don't have to have an ongoing exposure for silica and asbestos to continue to cause damage, because your body does not do a good job of removing them. Of course, concentrations, I can look up the TLVs, the PELs, the RELs in the pocket guide or in the booklet in the back of your textbook. When I talk about particulates that cause pneumoconiosis, they may cause scarring or damage, but they can also be what we used to call nuisance dusts. They're materials or particulates that don't cause any particular systemic problem, but their mere presence over time, if there's enough of them, can cause harm. Those are called, as ACGIH calls them, particles not otherwise specified. OSHA calls them particles not otherwise regulated, and NIOSH calls them particles not otherwise classified. And essentially they're dusts in the air that you can breathe in. Now, when we talk about particulates in the air, a lot of times the standards, the original standards, are what they call total dust standards. Total dust wasn't really total dust. It was dust that was collected in a 37mm cassette. But it was the standard method for collecting dusts for a long time. It's the sampling method by which most of the particulate standards that are currently on the books as far as OSHA is concerned are based on total dust samples that were collected over the decades prior. Since the late 70s, early 80s, we've started collecting what we call physiologically rated size fractions. So we did last week, we collected a respirable sample, because we know that certain dusts cause their toxic effect if they reach certain targets. And so we look at inhalable dust, thoracic dust, and respirable dust, going from large to small. And we'll talk about those in a little more detail in a second. The size of the particulates in your breathing zone, 1 micron is about 1/25,000th of an inch, very small. You can see with what they call specular reflectance, which is the light shining off of the dust mote, down to about 50 microns in diameter. If you ever looked at a window or where the sunlight was shining through, you could see little dust motes floating in the air. Those were probably down in that size range. The least particle, the PNOC, we've already hit on that. And the key thing is where the particulate is deposited determines whether or not it will contribute to illness. AED, again, I always bring up AED because it's important. The sizes that we talk about when we talk about our physiological size fractions are all in AED. When we talk about particles in general, we should be talking about AED, not their actual physical size or their apparent size. They're one of the methods that are used to see particles is by laser light and scattering. The problem is those see the actual size rather than the aerodynamic size, and they're not always reflective of what the hazards those particles may present. The adjustment for AED, the shape factor, obviously we're trying to adjust it so that it's a sphere. So it's a sphere, the adjustment is 1, right? There's no need to change it. And then you can see cubic goes on up. Fibers, you notice it says something greater than 1. Fibers don't really fit with this system, okay? Asbestos is fibers. Asbestos is still counted as fibers optically. Doesn't follow some of the conventions that we're talking about with regards to particulates in general, in part because fibers have a long aspect ratio, 3:1 or greater, which means the length is at least 3 times more than the diameter, which means that If it's falling on its side, it behaves one way, and if it's falling if it's sort of straight up, it behaves differently, and we can't readily predict how it's going to behave or where it's going to deposit within your lung system. And so fibers are kind of emitted from these other things that we're talking about. Now, those physiologically related size fractions, again, inhalable, thoracic, and respirable. It has to be inhaled first. Inhalable particles are particles that will come into your nose. They have to be less than 100 microns AED or less for us to consider them to be readily inhalable. It has a center point or a cut diameter. This varies a little bit depending on which chart you look, but it's right around 50 microns AED. Now, once I've inhaled it, it's possible for some of those particles to get down to my upper airways and middle airways, the thoracic region, your chest, the bronchi and bronchioles. Those particles have to be less than 25 microns AED, and they have a center point or a cut diameter of about 10 microns AED. And then the finest stuff, the stuff that can get down to my alveoli, which is particularly important for things that have systemic effects because there's much more blood flow, much more readily absorbed because the alveoli are designed to allow things to get in and out. Those things that are less than 10 microns, it's only about 1% of these guys, with a midpoint of 4 microns AED, can get down to my deep lungs and present that risk. So when I look at my standards, depending on the health effect I expect to see, I may have a respirable dust standard, I may have an inhalable dust standard, I might have a thoracic dust standard. And if we have not collected enough data to be able to define it that way, it's going to be an old total dust standard, although there is a movement to slowly replace all those old total dust standards. If I look at that graphically, I can kind of see how they look graphically. Now, when we talk about these particulates, we're talking about clouds of stuff in the air. We're not talking about any individual size, any individual particle per se. In much the way that we talked about populations and dose response, we're talking about groups, clusters of particles here. And so inhalable is kind of here, thoracic, so it has to be inhaled. This stuff here gets collected in my head and upper airways. The stuff that falls under here can get into my thoracic area. The stuff in here gets collected into my thoracic area. And then this stuff can get down into my deep lungs, the stuff down here. And so that's kind of what it shows. This is an old chart. It's 1997. You should have a more recent one in the back of your textbook. I've just not had a chance to scan and modify this in, but you can see about 1% at 10 microns for your respirable. It's the cut point for your thoracic, and about 77% of 10 micron particles are inhalable. So not even if it's a 10 micron particle, that's which is a factor of 10 smaller than what I can inhale, doesn't mean that it's going to safely make it out of my upper airways. Only 77% of them actually do. And so you can kind of see where things go. So what is total dust? I've talked about it as being the result of sampling with a cassette. Total dust is kind of a cloud of particulates that's less than 50 microns in size, and something larger than most thoracic, but something smaller than inhalable. It kind of falls in this range here. When side-by-side testing was done with inhalable methods, which has a well-defined curve, and old-style total methods, the ratio of inhalable to total, so inhalable is always greater, ranged from about 13.5 to there were a couple industries where the fractions were, the total was slightly higher, where it was 0.8 or 0.9, with an average of around 3.5. So on average, if I go out and sample in workplace, my old total dust samples in inhalable, my inhalable is going to be about 3.5 times higher, which can be a problem if I'm trying to use inhalable and comparing it to a total dust standard, which means that I'm not necessarily comparing apples to apples when I do that. So I've got to make sure that I collect the fraction that's appropriate for comparison to the standard. Otherwise, I'm not comparing comparable things. So biological reactions. We're going to go through this in a little detail. Pneumoconiosis is damage to your lungs simply from clogging up of your airways and processing of material. That accumulation of particulate matter can result in fibrosis, which is scarring of the tissues. Scar tissue doesn't work as well, and if I get scarring in my alveoli, a lot of times the alveoli thicken, which makes it harder for that gas exchange to take place. Bronchitis, which is inflammation of the bronchi. A lot of times bronchitis is a result of overproduction of mucus. There are certain compounds like vanadium that cause my body to produce an excess of mucus. If you've ever taken an expectorant, it's a medical treatment that's supposed to do the same thing, is to try to get your body to produce more mucus to try to clear things out. Asthma is a constriction of your bronchial tubes. Your body has a natural protective mechanism that if you're come in contact with an irritant, your bronchi will constrict to try to prevent it from penetrating deeper into your lungs. An asthmatic, a lot of times, they respond to a lot more things, and then the bronchial tubes don't release, and so the asthmatics have a hard time breathing because they're trying to breathe through narrowed airways, air passages. Of course, cancer-causing agents, and then in extreme cases where I have damage to my lungs and my lungs not working as well, my heart tries to make up for that by beating more, and that can result in damage to my heart as well. Pneumoconic agents, pretty much anything that you can get into the air can cause a pneumoconiosis. Pneumoconiosis is kind of the generic term associated with exposures. Metal fume fever is a disease associated with exposure to fumes of light metals. It's not uncommon to see it in people that do welding. If you don't use proper respiratory protection or ventilation, they get exposure to enough of these light metals. It causes a flu-like condition. They feel like they have the flu, usually the next day or shortly after they've been exposed to these metal fumes. Chronic exposure to these over time can cause additional damage to their lungs beyond just that fever-like response. You can have systemic effects where the material gets absorbed. It can be an inorganic material, or it can be an organic material. It gets absorbed into the bloodstream and passed elsewhere. Remember, a systemic effect is one that occurs remote from the site of absorption. You can have allergic or sensitization reactions. Some are man-made chemicals like isocyanates that can cause allergic reactions. Others are naturally occurring materials like wood dust, smite feces, pollen. Anybody that has seasonal allergies, of course, is familiar with pollen. And then some that we've identified long enough to go that we've actually given them their own names. Cotton brack, which is the covering or coating in cotton, causes bisonosis, and exposure to dried sugarcane dust can cause what's called bagasosis. Thermophilic actinomyces, they like to grow in haystacks. If you have a haystack with moisture in it, you can stick your hand in it and it gets hot and will actually combust if you have enough moisture in it. But when you turn those over, you release large clouds of this species, and that could cause a disease called farmer's lung. Bacterial and fungal infections. So these cause allergic reactions, allergic and sensitization. That's different from an infectious agent that can actually cause an infection that you have to treat with your immune system's responding to try to treat it. Anthrax gets a lot of press because it's been weaponized by countries, but anthrax also occurs naturally. The natural anthrax is actually usually causes ulcerative pitting of the skin, but it's readily treatable with most antifungal agents. Grain aflatoxin mold, and a few other there's the Mycobacterium tuberculosis is the bacteria that causes tuberculosis. It is the most common disease worldwide in terms of morbidity. In other words, individuals that are infected with the disease. And then a couple other notes: Legionella, which is associated with the outbreak of sickness and death at a Legionnaires' convention in Philadelphia in the 1970s, and hantavirus, which is a disease carried by rats that's been prominent in the news for New York City and Los Angeles lately. Irritants, anything that's caustic, acids or alkalis. Acids, of course, are low pH materials. Alkalis are high pH or bases. Other mists that have irritant effects, like chromates. Certain chromates, hexavalent chrome, also is a known human carcinogen, so it has a different exposure limit than the other ones. And then, as I mentioned earlier, the vanadium compounds, which can produce that overproduction of mucus. You can also inhale radioactive material, alpha particles from alpha emitters, or radon, which is a radioactive gas that then decays into a solid. Inhalation of these can result in radioactive exposure. We're going to talk about ionizing radiation exposures a bit later in the book, so I'm not going to talk about it right now. List of hazards. We talked about the isocyanates. They're used to make paints and mastics and glues. Diesel exhaust, of course, anytime you have a diesel engine running, that soot that's associated with that diesel exhaust has its own regulatory standard. And surprisingly enough, certain wood dusts are now considered carcinogens. And so depending, we have to identify the species of the wood dust to make sure that we're properly taking care of that. Of course, radon and its progeny, daughter decays. Sodium hydroxide, which is a strong caustic material. Silica quartz and cristobalite and tremolite, which are other crystalline versions of silica. And kind of a list of things that we can talk about. Silica and asbestos are unique in that they both cause what we call progressive fibrotic lung tissue. They cause that continued damage and scarring to the lung. They're not readily cleared by the lung. It takes the body great effort to get rid of them if it can get rid of them. And so once you've been exposed, the damage from exposure continues to progress. Well, hence they're called progressive fibrotics. Asbestos is a fiber. Asbestos has its own standard, in part because fibers, as we talked about earlier, don't behave the same. So while we have talked about ppm for gases and vapors and milligrams per meter cubed for our particulates and aerosols, asbestos is fibers per cc. A cc is a milliliter. So the standard 8-hour time-weighted average for asbestos is 0.1 fibers per milliliter of air, cc of air, or 1 fiber for a step. So it's awfully low. Your book also kind of goes through some of the different filters that are used. I wanted you to be aware of this, but you don't have to get too in-depth on it. We also kind of use the NIOSH manual analytical methods in the lab to kind of help you get you a little familiar with the different types of materials that you might use to collect samples in the workplace. Now, when I'm using a filter to collect a sample, or if I'm using a filter on a respirator to protect my worker from exposure, there are 5 primary mechanisms of particle disposition that I need to be aware of that are affecting how well that particle is going to be collected. Notice there's 6 things on the slide. That's because interception gets to be on there twice. Most of these are based on what's called the single fiber theory of particle deposition. And basically what it is that single fiber is that round thing you see in the center. It's supposed to be a fiber on your filter. And the concept is that in order for something to be collected, it must come in contact with the fiber. And once it's entrained on that fiber or attached to that fiber, it won't become re-entrained into the air. So the mechanisms are inertial impaction. And basically in that case, the air comes along in much the way that both our slit impactor and our cyclone worked. The airstream turns, the particle can't make the turn with the air, and it gets carried forward and gets collected. Just like our cyclone collects it on the wall, or inertial impactor collected it on the slide. Sedimentation, the particle is so large that the air is not moving fast enough for it to stay in the airstream, and gravity pulls down on it and it settles out and gets collected. The particle travels along with the airstream just fine. It doesn't settle out like it does up here, but it sticks out from the airstream enough that it touches the fiber and gets collected. That's simple interception. The complex is the particle's too big to make it between the fibers. So this is actually why I have two fibers. And then the other two, which are really mostly for smaller particles, electrostatic attraction. Fibers, the materials tend to be positively charged. Aerosols tend to be negative charged. Opposites attract, and so they get drawn to the surface. And the last one, which is really affects protected for gases and very fine particles, is diffusion. Particles tend to move. They don't stay in one location. They tend to move from gases move from high concentration to low concentration by diffusion. Particles kind of move around in the same manner. And if that random motion carries it to the fiber, it gets collected. Now, when I look at those, as my particles get smaller and smaller, the predominant mechanism of collection is diffusion. So it's got a little chart out of your book. One that I like a little better is this one. It shows the kind of combined collection effectiveness. And if you notice that there's a minimum point where things are not collected as well. This usually occurs around 0.3 microns, plus or minus. It's called the nadir point. The nadir point's important when I'm talking about using filters to collect things or protect my workers, because I need to make sure that I'm collecting the particles I think I am. Nadir point is the low point, the minimum point at which these things don't collect very well. And so if I can collect the particles well here, the theory is if it gets smaller, if it gets larger, I'm going to be able to collect it even better. Now, there are a number of other types of size selective samplers out there. We're not going to spend a lot of time talking about these. I just wanted you to be aware of them. They have cascade impactors, where basically you have a series of stages. The most well-known is an Anderson impactor, where you have stages, and the holes in the stages get smaller and smaller, and below each stage there's a platform where the particles impact, very similar to our slit impactor that we talked about. Since the holes get smaller, the velocity of the air through the hole increases, so I get smaller and smaller particles that can't make the turn as I go down the cascade. A virtual impactor does the opposite principle. It keeps a main stream through the center. The particles that can diffuse and move away do. The stuff that has to remain in the airstream gets carried down further. I'm not going to go into the math, but these both work. The Respicon, which is designed to collect inhalable, thoracic, and respirable, you can get all three, is a device that's used, a virtual impactor that's used in workplaces. And then you have particle counters. I talked about those earlier. There's different ways of counting the particles in the air. The problem with particle counters is they give you the physical size for the most part, although time of flight can sometimes give you aerodynamic size. And so sometimes the particle counter's data does not readily translate back to those physiological size fractions. Those physiological size fractions are what I'm trying to get a handle on, because it tells me whether or not, or the degree of hazard that something presents. Because if it has to be absorbed, if it has a systemic effect, and it gets taken out in the upper airways, it presents less of a hazard than if you can get to the deep lungs where it can readily dissolve and be transferred. So, as I said earlier, ACGIH, and I think NIOSH is on board with this as well, has an intent to try to change all of their old total methods, using that cassette that we talked about, into physiologically related size fraction methods inhalable, thoracic, or spiral, depending on which is appropriate for the type of exposure. And they have called for, and they've been calling for this for about over 20 years now, to collect side-by-side samples using total and the physiological size samplers to be able to adjust those standards. A standard that is for total dust is not really applicable to samples that are collected inhalable, thoracic, or respirable. In the same token, a total dust is not necessarily going to tell me whether or not something that presents a greater risk as inhalable, thoracic, or respirable is safe relative to the size fractions. The total dust just isn't really comparable to these guys. So we need more data. And one final note, I spent a lot of time talking about particulates. Going forward, we're going to talk about gases and vapors in our next section of materials. Things don't happen in a vacuum in the workplace. You get exposed to not just one particle or one particle size, but a cloud of particles. And those cloud of particles may also have gases and vapors in them. And so I have to consider when I'm collecting, particularly if it's a spraying operation, what state the matter might be in and what that means in terms of my exposure to that hazard. And also, how can I readily or accurately collect that sample? The rest of this is a list of references if you want to look up some of this information. If you decide that you really like the aerosol stuff, I highly recommend Heinz's aerosol technology properties. It is the best explanatory book. It actually explains things in a clear manner, even though it covers a lot of technical issues, in a way that you can understand it readily. Some of the other things, if you read through the book, you'll see it gets kind of deep in the weeds, technical-wise, pretty quick, and it may be very difficult to kind of understand some of those things. So that's it for particulates. When you do your homework assignments, I stopped at page 200. There's more stuff after that, but it gets very technical about how they sample, a lot more detail about asbestos. It's interesting and useful information, but it's very technical. And so I didn't feel it was really fair or necessary for you guys to have to go into that much depth of particulates in this particular class. But if you're interested, I highly encourage you to go ahead and try to read that material.